Where were we at? So last class, we started talking about gases. So I want to point something out because I don't know if I made it clear on Monday. So what we did is we talked about what's called Boyle's law. Now, what does Boyle's law say? Basically, in mathematical language, it says this. It says if you have a gas and it's at some initial pressure and takes up an initial volume, which we'll call P1 and V1, what happens then, if you change the pressure or you change the volume, then the new volume or the new pressure, they must satisfy this relationship. So let's say in sort of in English what we mean by this. So in English. So if this is our Boyle's law mathematical description. So if you take a sample of gas, and I'm going to put gas in parentheses, and the reason I'm doing that is, if you remember, we did not define gas at all on Monday. In fact, I told you I want you to ponder what is gas. I mean, we all have our intuitive idea of what a fluid is, or what a solid is, or what a gas is, you know, these fundamental states of matter, if you will. But we really didn't give it an actual definition, and that was by design. I want you to think about that. But you all have, I think we all as humans have an intuitive understanding of what a gas is, at least in a naive sense. And that's really all you need to think about right now. And so you take a sample of gas, and what we stated is there's four quantities that we use to describe it. And the four quantities are temperature, pressure, volume, and this number of moles. And so let's imagine in an ideal world, or in a fixed environment, we can take those four quantities and keep two of them fixed. So if we take a sample of gas and fix the temperature so it can't change, and we fix the number of moles, and then what we say is we say that volume is inversely related to pressure. So what do we mean by inversely? What does that have to do with, you know, the English description and the mathematical description? For those who are fluid in the language of algebra and mathematics, that whole sentence that I've written in blue is encapsulated in this red equation. So let's think about why that's the case. And by the way, you got to remember where this stuff comes from. What happens, again, let's not forget how science in sort of in a very generic way works. Scientist has an idea, a theory, and a hypothesis, if you will. And then they go and they do an experiment. And usually in experiments, they are controlled environments. For example, Boyle may have been controlling temperature and number of moles, or at least attempting to. And what happens is when scientists like Boyle and other scientists at the time who were studying gases, what they realize is they recognize a pattern. If pressure does one thing, then volume does this, and vice versa. And if you look at that relationship in a, say, graphical sense, if you know, back when you were in middle school and in high school, you learned how to graph data using a coordinate axis. I mean, we talked about that way back on day one. If I draw a coordinate axis, and this, again, I'm not trying to frighten us, but let's think of it this way. We have some coordinate axis. And so let's look at our equation, and I'm going to write it a little different. Instead of writing it as P1V1 equals P2V2, I'm going to write it as V2. So my new volume, how is it related to my old volume? Well, before I had P1V1 equals P2V2. So if I solve for V2, what I end up having is I'm creating my own English. I have P1 divided by P2 times V1. So if I just rewrite the equation like this, let's think about what happens. So we might think of this as, and please don't get too frightened. If you want to look at a similar thing, let's imagine that we have an equation like this, y equals mx. So this is what's called a linear equation. It's a line with slope m. And so we can visualize this Boyle's law, the mathematical formulation. If we label one axis, we'll label this. So let's think about how we want to do this. So if we want to keep the analogy with y equals mx plus b, which is, well, okay, maybe we'll do it. It's slightly different. Let's, maybe I'm being more confusing than I should be. Let me get my eraser. So, excuse me. Maybe I'm simplifying it a little, getting sort of sidetracked more than I want to. So think of the horizontal axis. Think of the horizontal axis as pressure, and think of the vertical axis as volume. So what happens as let's imagine that the pressure increases. So if I go from an initial pressure, and as it increases, what happens to this number right here? So let's look at this fraction, P1 over P2. If I have a number P1, I have a positive number, and then I enlarge it to be P2. So think about this. If P sub 2 is bigger than P sub 1, then the fraction is less than 1. I mean, think of your fraction. I mean, if you have 7 over 11, that's less than 1. But if you have 11 over 7, that's greater than 1. So if the pressure increases, what does that force the volume to do? Well, it forces the volume and the pressure to have this sort of relationship. It forces that as P gets larger, the volume must shrink. So again, let's think about that. If P increases, and that means P2 is bigger than P1, what that says is the volume decreases. So that would mean V sub 2 is less than V sub 1. So there's a few ways you can think about that looking at the algebraic formula, and I hope that you do. Will you? I don't know. Does anybody have a question, comment? Probably not. You guys don't say much. Very, very quiet type. Very quiet. Scream and yell. Okay. Okay. So that's the so-called Boyle's law. And then we did an example that, as we commented on, it kind of was just like this weird example where we talked about how long an oxygen tank lasts. And as I pointed out, and I'm going to point it out again because it should be said, I don't think enough times in math class and in physics class that the truth is set free, so to speak. Oftentimes, problems we're doing are just concocted, simple, what we call textbook problems to help you work with a particular topic. That's it. So, you know, as I said last class, you're never going to be sitting in a hospital room, you know, calculating on a calculator how fast the fluid is moving. Well, maybe you are. Maybe you're interested. You want to know the speed of you know, fluid moving through an IV tube or through a needle, a syringe. But what we're telling you is you can. And some people do have to worry about these things. I mean, if you're building medical devices to assist in breathing, well, then you'd have to understand how pressure and gases work. I mean, think about the lungs. If you inhale and exhale, how your lung capacity increases and decreases. How does that change pressure? So, you know, this stuff is not just to learn for nonsense. It's just most of us learn it in school, and that's it. Well, there's few of us who use it on a daily basis. But nonetheless, I feel like it is something that we should at least learn and do once in our lives. So, very good. Okay, so let us move on. And by the way, we're sort of building this historically. I mean, one way to teach gases is just to write down what's called the ideal gas law and then work from there. We're going the other way. We're building up these experiments or these laws based on, you know, the experiments and when they were discovered and in sort of in a historical context. Okay. Very good. So any questions, comments before we move on? Good. All right. So all right, what's next? So Charles' law is next. So if we write this down in math first, we'll get the bad news out of the way first. So the bad news is we have to understand it in a mathematical language. But what does it mean in English? So what it means is volume is proportional to temperature. And we have to be very clear here. We're going to use what's called absolute temperature. So we haven't really discussed that word, but and we will in due time. But the way we're going to take it right now, at least what's important for you to understand, is this means we're going to use Kelvin units. So, I mean, most of us are familiar with Fahrenheit because we live in the United States and we use it. The rest of the world uses Celsius. And then there's a third unit that is often used in science, and it's called Kelvin. And if you're not familiar with what that is, a degree Celsius is Kelvin minus 273.15. All right, does anybody have a question about this? Maybe, maybe not. Oh, Charles's law. And by the way, some people put the apostrophe here. Some people, I guess this is technically wrong because it is Charles's with an S. Let me fix that. I should know better than that. I should be fired. Guess we should do it like this. Some people actually put another S after the apostrophe. It just depends on where you read it, I guess, or what convention you take. So what does the sort of the picture look like for this? Well, if we're going along the lines that we did before, if we want to think of a visual of what's happening, if I take my XY axes or my coordinates, and again, this time I'll put temperature down here, and then we'll have volume. And so what happens if you look at the relationship, if you take V1 over T1, and we know it's equal to V sub 2 over T sub 2. You can write this and just do a little bit of algebra, and you can write it in a different form. And what would be the different form? We'll say we write this as V sub 2 equals what? Well, it would be T sub 2 over T sub 1 V sub 1. And so what you notice happens if T sub 2 is bigger than T sub 1, if temperature increases, then volume will increase, because this number, once again, right here, this fraction is greater than 1 if T sub 2 is greater than T sub 1. So if the temperature increases, then what that means is volume must increase. So if you look at the graph, it's going to look like this. It's going to be a straight line. So when we say that they're proportional, what that means in math sense is that means there's a linear relationship. Now, of course, don't forget this is all under controlled conditions. And so note what this means. I know we didn't say it in the previous slide, but it's worth pointing out again. This means pressure and moles are fixed. The only thing we're allowing to vary is temperature and volume. So in a naive sense, this is one of the, I shouldn't say one of, but in a naive sense, using Charles' law and Boyle's law, you might start to think about how things like your car tires behave when the temperature changes, that kind of stuff. I know, I always think of that. That's the example in my head all the time, especially now when your car has most new cars at least have a warning when your pressure drops. Some cars actually tell you the exact tire pressure. Okay, so this is Charles's law. Okay, so fun times. Okay, so let's before we move forward, let's sort of reset and remind ourselves of, again, these Charles' law and Boyle's law, they're simplified, what we call models. Do they precisely predict how things behave? No. In fact, they're very limited. But that's how science works. I mean, I always like to use this sort of the idea. I mean, the first boat that was ever built wasn't like a cruise ship, right? I mean, one day someone was like walking through the woods and they saw like a tree fell on the water and they're like, oh, it floats. And then one day someone else had the idea, well, if we take a couple of these logs and tie them together, we can float down the river. And then eventually, after many, many years and people building on other people's ideas, we designed boats and flotation devices. Science is very much the same. I mean, if you want to understand gases, the first experiment that someone did to try to understand gases wasn't the experiment that figured everything out. I mean, these theories change over time. And so what we do in science is we try to build up, we simplify things. Boyle's law, we simplify it by trying to fix our environment. We only let two things vary. And then Charles' law is very much the same. We fix our environment and only let two quantities vary. And then the third situation here is what we call Avogadro's law. And you might remember Avogadro from chemistry, hopefully. Avogadro's number. So what does Avogadro's number say? Or Avogadro's law. So this is very similar to Charles' law in its algebraic structure. So if we fix temperature, that's exciting, and you fix pressure, then the number of moles and the volume tend to obey this relationship, at least in a controlled environment. So if we write this in English, volume is proportional to the number of molecules. So this makes little sense to us unless we have a somewhat of an understanding from chemistry about this kind of stuff. I don't know how little or how much you guys know. Some of you may know more of it than I do, others may not. It shouldn't hurt us in doing the physics aspect of it. But if you're confused on what a mole is and molecules. I mean, that's just a Google search away. Again, I believe you guys already had a chemistry class. Correct me if I'm wrong, but I think you did. So hopefully if you have questions, you ask. So if you looked at the algebraic, this algebraic equation, it's if you replace the n's with t's, it's just Charles's law, and so the physical picture, the graphical picture, I guess I should say, is a line. So does anybody have a comment or question? I like to just ask that, even though I know history says you won't. Face looks very rotund. Avogadro. By the way, you ever Google him? He is just Google him. His portrait. I guess they didn't have photographers back in like the 1700s, 1800s, but if I recall, his portrait makes him look like one heck of a human being. So if you want a nice, well, I don't want to say, you shouldn't laugh at that stuff. Google Avogadro. Amadeo. I think that's how you pronounce it. All right, anyhow, fun times. I believe he was an Italian. Avogadro's law. All right, good deal. Okay, so those are the three laws when we fix. The other two sort of characteristics of gas. And we can combine them, and when we combine them, we creatively call it the combined gas law. So you get the following: P1V1 over N1T1 equals P2V2 over N2T2. And so the point is if you keep one or more of these things fixed, if you keep temperature fixed, then T sub 1 and T sub 2 are the same number. And so you can cancel them from the equation. You can divide them out as you would have been taught in algebra class. If P1 and P2 are the same number, that is, pressure is fixed, then you divide them out. So this thing reduces to one of the other three laws when you hold two of the constants fixed. And so that's why we call it the old combined gas law. Very creative. So you could argue that you don't even need to learn the other three. You can just know this one, and then when the problem that you're asked to solve or the situation you're studying fixes constants, then you just cancel them out. Does anybody have a comment or a question? So these problems, I mean, it's funny because the example that we did on Monday was probably more complicated than any other example you'll be asked to do on homework and stuff like that. For the most part, these problems are very simple. It's plug and chug. And really the difficulty is usually one of two things. It's which formula do I use, and are my units correct? Do I need to change units to make something work? Does anybody have a question, comment, concern? I don't know. So let's look at a very simple example before we move on. So a certain gas, I guess I should be English grammatically correct. So it's not important for this example. So a certain gas, say, occupies let's say 500 liters at 25 degrees Celsius. Determine the new volume if the temperature increases to 32 degrees Celsius. So this is a routine, once again, textbook kind of problem. So the first thing we should do is we should figure out which law we're going to state or which formula we're going to use. And there's a couple things you'll notice, and I guess we'll write it like this to be, I think the book does it this way. I don't know. We'll see. I could be wrong. But either way, the first thing I'm going to note so I'm going to assume P and N are constant because they don't appear in the problem. Now, I could have just stated in the problem, hold them fixed, but and in the future I might and I might not, but you can just assume, I mean, if I don't state that as part of the problem, then they're constant. Okay, so the next thing that we should do is I mentioned this when we stated Charles' law, which had to do with temperature and volume. And so being that this problem gives two quantities and asked what happens to one when the other changes, we assume that Charles' law is the way to go. And we have to remember that for Charles's law, we should use Kelvin. So that's what we'll do. Let's get a different color here. So the next thing, so we want temperature in Kelvin. So we remember a few slides ago, we told you that relationship. So how are we going to get Kelvin? Well, if you start with Kelvin to get to Celsius, you subtract. So we need to do the opposite now. So if we started with, what did we start with? We started with 25 degrees Celsius. So we need to subtract. And, excuse me, not subtract, we need to add. So you need to take 273.15 and add it to 25. And when you do that, so what is our T1, our initial temperature was 25 degrees Celsius, and that is equal to 298.15 Kelvin. And then, of course, T sub 2, which was 32 degrees Celsius, if you do the arithmetic there. So 32 plus 273.15 is 305. Barring I didn't make any arithmetical errors. Kelvin. By the way, a good question to ponder is, why do we use Kelvin? Why can't we use Celsius? That'd be something good for you to, a good learning experience. And I would encourage you to think about it before you look it up. Although it is nice that pretty much anything you want to learn about now is a Google search away. Okay, so there we go. We have our two temperatures, and now all we have to do is plug and chug. So if we take, you know, Charles's law, let's write it this way this time. What does it say? Well, it says our new volume is our new temperature divided by the old temperature times our initial volume. And so we can plug these things in. We have what? 305.15 Kelvin over, what was it, 298.15. And then our initial volume was what? I forget already. I'm like having brain. 500 liters. So the Kelvins cancel. That's good. And then we just have to do some arithmetic now. Calculator fun. So what is 305? You go to a calculator and do the division. And then multiply the ratio of the temperatures by 500. We get approximately what? 511.74 liters. So as expected, if the temperature increased, our volume increased. So that's our new volume. Does anybody have a question about this? Comment. Comments, concerns? So this is, I know the example we did on Monday was a bit more involved in this, and we kind of rushed through it because we were broken up because we had the guest and stuff. So I apologize for that. But this is most of the gas, not most of the gas, but these are the kinds of problems you have to answer to, and these ones are much more direct and straightforward than what we did on Monday. So. Okay. Sweet. Let us move on. There's 10 of us in here now. We have grown. We're like a petri dish of bacteria. So here's an interesting fact. So under ideal, so let's make it clear this is not real world. So what does ideal conditions mean? Again, this means something like fixed environment in a laboratory or a fixed experiment. What we're saying is this is not necessarily how things will behave in a real setting, but at least it's good enough to predict in many cases what's going to happen. So under these ideal conditions, the number, and I want to be clear how I write this because I think it's useful to think of it this way. So the number P times V divided by the product NT. So if I have a gas, it's some fixed time. It has a pressure, it has a volume, it has a number of moles, and it has a temperature. So say we're in some laboratory and we're doing an experiment, and at exactly 7 seconds, I freeze everything and I calculate the pressure, volume, number of moles, and temperature. No matter what, this thing is a constant. We denote by R. So what does that mean? If we're going to say it's a constant, we say PV NT equals this number, R. So if we solve this, and I guess, well, before solving it, because it's usually not written this way. Perhaps I should reiterate what I said just so we don't go too fast. So again, imagine we're doing an experiment. We have some gas we're studying. We recognize its volume, its pressure, the number of moles and temperature can be changing. But what we say is that in an instant, we want to ask, what is this number, PV divided by NT? And what we recognize is it's always constant. It doesn't change. Again, if we restrict ourselves to what we call ideal conditions, and so one of the things I guess I sort of get questions about, I don't get many questions right now because you guys don't ask much, but I guess it's different when we're sitting in a classroom and you feel more obligated to be a part of the fun, is why R? Well, I don't know why they write this number as R, and R has a name, and what is all this? You know, some of you are just thinking, what does all this gibberish even mean? Again, I'm trying to give you context for what we're trying to do here. I mean, remember, at the end of the day, the idea is to describe how gases behave. Now, you might say, I don't care about how a gas behaves. Well, right, but we're telling you if you did care, this is one of the simplest models to explain the behavior of gases. And it works in many cases. It just doesn't work in all cases. So this is what we call in the ideal cases. Okay, so so this number R has a name. And it's called the universal gas constant. Or the ideal gas constant. Whatever. Now, the interesting thing about this number is if you go to the previous screen, it's equal to a pressure times a volume times the number of moles times the temperature. So what you have is you have 4 different units on the left-hand side of this equation. You know, how do you want to, we didn't really get into it, the specific types of pressures, but we've asked you to use at least a couple different ones, PSIs and pascals. And then we know with volume, it can be liters, it can be cubic feet, it could be meter, whatever. There's all kinds of different units for volume. Temperature, we know there's 3 now: Celsius, Kelvin, Fahrenheit. And the number of moles, what is that? Well, mole itself is a unit, if you remember your basic chemistry. And so there's lots of different units for this number R. So one of the things I always find funny, I always ask you this, it'll be on like your final, what's your favorite version of the universal gas constant, or the number R? And if you go to the Wikipedia page, they list about, I don't know, probably 15 or 20 right at the top. So so one of the more standard ones that we'll use is the following. And by the way, this number R, when we say it's constant, I guess maybe it's not so clear for some of us who are not mathy and physicsy from the get-go, but that means it's the same for all the gases. And so this number is going to be used for oxygen or for whatever nitrogen, whatever gas you're discussing or using. They all have the same universal gas constant. So what happens is, if we all, as a universe of scientists, if we all agree on a certain, what we're going to call standard conditions, if we say, okay, let's call, just like, think of it this way: we all agree in physics and in math that when we have a graph, that we agree that up is positive and down is negative. And then if we go right, that's thought of as positive, and left is thought of as negative. Those are conventions. And so we have to choose conventions when we're doing physics, like in this class, and we're talking about objects that go up and down. Well, if I say you're moving at 3 meters per second, well, how do I describe if that's going up or down? Well, the way we assign direction is through what's called up is positive, down is negative. And so that's a convention. We all have to agree on the same convention, or if we don't want to agree to use the same convention, we all have to be understanding that your convention might be different than mine. And so anyhow, what happens is if we agree on what we call standard temperature and pressure, we can calculate R. So, I mean, this is something that if you wanted, you can Google. If you just went into any search or any internet browser and just type standard temperature and pressure, it's going to autofill automatically. And the first hit you're going to get is likely a Wikipedia page. Let's see, what I just typed it in. What did I get? Oh, I got an engineering page. And there's a chemistry page that these things pop up. And so what is the standard temperature? We all agree that it's 0 Celsius, and then we're going to call that the standard. And basically this is sort of a way for us to all come to a convention on how much or how much space, I guess, a mole occupies is a better way of thinking about it. And so your book goes through the derivation. I would encourage you read it or go find it on the internet. And so if we do that, one way we can compute R is we can compute it to be 8.314. And then this is joules divided by mole times Kelvin. So this is one of the more common, this is one of the more common SI units for this number. So that is the gas constant, or the universal gas constant. And so what we usually do is we usually rewrite the formula in the following way. So PV equals nRT, instead of writing it as R equals. And this is called, as many of you probably know already, the ideal gas law. So once again, we've built up to this. We said, okay, or at least, well, I don't say you said it or I said it, but I'm saying as a scientific community, you start by studying 2 quantities at a time. We'll study these 2, then these 2, then these 2. And then what you realize is that you can combine all these to one formula. And as long as certain conditions and hypotheses are met, we can predict the behavior of gas somewhat using this formula. How accurate this formula predicts gas behavior depends on what our conditions are like. Is the temperature too high, too low? Does anybody have any questions, comments? So another way to think about these formulas is the three laws that we stated already are because of the way the nature was, where we had two volumes and two temperatures. You can think of those laws as studying what happens under changing conditions, whereas you might think of the ideal gas law as trying to figure out what's happening at a moment in time, not as things are changing, but at some specific time. So for example, a common textbook problem would be to, can you find the weight of a particular gas? This could be something. I'll go back to the example we did on Monday. Maybe we have a different problem. We have a cylinder of oxygen, and we say that it has this much volume of gas and it's at this pressure. What is the weight? How much does this cylinder weigh? So these are the kind of problems that we'll ask you to do. They're not terribly difficult, and when you get stuck, we help you with them. Does anybody have any questions about that? So the next step, does someone have something to say?
Yeah, I was going to say, so like by using the weight of the cylinder, we can kind of approximate the number of moles.
Well, what do you mean using the weight of the cylinder? Yep. I mean, you just mean the metal itself, or whatever the material is, plastic or metal?
I mean, you zero out the metal and the barometer and all that good stuff, but then, you have oxygen's weight, there's only oxygen in the cylinder, and we can approximate.
Right, but don't forget that the oxygen's weight will depend also. I mean, we're going to give you a problem like this, but the oxygen's weight is going to also depend on the number of moles, right? So, and look, these things, again, the same, we talked about this Monday, I think, Andrew, and I don't remember if it was you that asked it or not. I mean, these are simplified problems. We know in the real world that the weight is going to vary because the tank itself has weight. There's atmospheric pressure on the tank. But if we're just talking about a more simple thing, like how much does the oxygen inside the tank weigh, then that's a different problem than talking what is the force on the floor of the oxygen tank. Does that make any sense? Because clearly there's a lot more happening. If we're studying how much pressure or force is being placed on the floor by a tank of some gas, that is completely different than if we are just asking about the weight of the actual gas inside. I mean, to simplify that question a little more, go back to when we did fluids. The first thing we did is we said we have like a cup of water, and then we said how much force or what's the pressure of that water on the bottom of the cup. And then we realized right away, well, that's only answering one question. That doesn't give us the full picture because we know the atmosphere is pressing down as well, right? So again, this is where as you guys already is working, people who medical, and you're in the medical field, you're working already. And now we're saying, okay, here's these textbookish problems that aren't really, I mean, for the lack of a better word, they're not, these are simplified versions of what's going on that you would see in an operating room or in whatever, right? And so in many cases, you might feel like we're asking you to like go backwards. You're like, who cares? Like, I'm not going to think about this. Or and also, as you already know, there's certain things that you do as professionals that you already know, tricks. I don't want to say tricks, but ways of sort of things that humans have figured out over the years that you can do to compensate for, hey, if I read this gauge and it says I can say certain things about what's happening. I don't need to like go to my notebook and calculator and do a physics problem. And maybe that's sort of what you're alluding to anyways. But you do have to be careful about, like, we didn't say much about it, I don't think, and maybe this is more along the lines of your questions. There's different things too. You have absolute pressure, you have gauge pressure, these kinds of ideas, and distinguishing between them. And don't forget as well, we are trying to mimic real world scenarios with simplified versions. So Obviously what's happening in a live, say, operating room where things are varying constantly, we're not going to get, we have no idea how accurate these things would be, right? It's not a controlled environment, even if you'd want it to be. Temperature goes up and down. I guess you can control some environments. But yeah, I don't know. Did I answer your question, or maybe I interpreted your question incorrectly? But
Probably the latter. So let me give you an example.
okay.
An oxygen tank is like the best example we have because it's a fairly well-known volume. The pressure fluctuates with temperatures and
Correct.
yada yada. So like when I was out on the flight line, we would have temperatures ranging between, pretty much freezing and then 110 on the hottest day. And all we really had to go on to know how much oxygen was in our cylinder was technically the pressure gauge.
Yeah.
And the pressure gauge at 32 degrees is a lot different than the pressure gauge at 110.
Correct.
Fahrenheit, both Fahrenheit, obviously. So what I would see my partners do all the time is pick up the cylinder and see how much it weighed. And because they had picked up so many cylinders in their life, they kind of knew which one was full and which one was empty.
Yeah, you can actually. That's funny you say that because it's an interesting thing, and there's no doubt about that. It's no different than if you cook with propane grills all the time, and you can gauge how much is in there by checking the weight on it. Or you can check. You can look at the gauge. I mean, I don't know how familiar you are with like a kegerator or sort of using that kind of thing for a barrel of beer. But the same idea is you can look at the pressure and then pick it up, and you can gauge the volume that's left based on those ideas. And I don't know this to be correct. I don't want to speak out of turn but I would imagine that you can actually quantify that using something. Well, at least for gases, you could probably use the ideal gas law to quantify that. So that wouldn't be a bad thing to do. Maybe we can concoct a problem that would allow you to do that. But you're absolutely right. I mean, that would actually be a good experiment if we had like a laboratory session of this to collect data. And I bet you, again, I don't know this to be certain, but I would bet you can quantify that exact thing pretty precisely using these ideas, right? Because again, it goes back to what I said before. When you're doing an injection, you ain't worried about how fast the medicine's going in, right? Now, of course, if you have an IV, you might be, or a drip rate or something, that's a little different, but just the same thing here. I don't think you're staring at an oxygen tank wondering how many moles are inside of it at any given time, right? That's probably not on your mind, nor should it be at that point, right? But the fact of the matter is, if we want to understand, I mean, our job is to learn a survey, a fundamental understanding of basic physics, right? And so whoever the people are on this planet over the last 100 or so years that decided what that means, this is the kind of problems we're going to ask you to do. Even though, again, it's like anything, will you ever be thinking about it in real life? I highly doubt it. Right? You're more likely to use, your common sense to understand these things, like picking something up or feeling how cold it is to mix. Right? So anyhow, but yeah, your point's well taken. Yeah, look, that's the downside to my job, right? My job as a mathematician I teach some physics classes as well. But most of what I do is I'm trying to sell things that are interesting to me to people who don't really give a damn, right? And that's okay. You don't have to. I find this stuff interesting. It's a curiosity to me, much of which, now there's some of you might actually be interested in this. I don't know. I don't expect you to be. You're here because the world says you have to be, right? Just like I teach tons of students who are going to go on to be engineers, and they have to learn things that they'll maybe will or will not use. Going to be computer scientists, and they maybe will or will not use it. And then there's people, that's the hard thing. I have to, it's hard for me to convince you that this stuff's useful when I know some of it is and it isn't. So most of why this stuff is useful is because it helps your problem solving skills. I do believe that, but do I think that you need to know how to calculate the number of moles in an oxygen tank? No, I don't think you need to know that. I think your common sense can tell you certain things like you're suggesting, right? So anyhow, I don't want to keep going on that horse. That's just sort of the relationship that we have to have. I have to get you at least somewhat interested in learning things that, for whatever reason, you might not be, and that's just the way it is. That's fine. I took classes that I had to learn things I didn't really care to, and I survived. Hopefully you guys will too. But anyhow, we're going to give you a bunch of problems to do with this stuff. Some of them will be very easy. Some will be a little trickier, and then we can talk about them on Monday. Do you guys have any other questions, comments, concerns? Again, I will try to get those grades posted ASAP. I just, look, I not that you guys are my least favorite, but you guys are my least concern as far as getting that up. I mean, if you turn the work in, most of what I've already seen is good. So, anyhow, and if you have any concerns, just hit me on an email, and we'll hopefully alleviate any concerns. All right. All right. Well, listen, thank you guys. If you have questions, please ask. Otherwise, I will talk to you Monday. Have a good weekend, and be safe. Stay away from the Rona, if you will.
Thank you.
Yeah. All right, everybody. Thank you guys. Take care. Be safe.
Thanks.
Yep.
See you.
Thank you. Yep.